So determine whether B can be written as a linear combination of a sub 1 and a sub 2. Right? So what that's saying is, can I define a set of scalars that would allow for B to result from the sum of a sub 1 and a sub 2. All right? So what I'm going to do is create some arbitrary scalars. I'll call it C. C for scalar. I'm going to say C a sub 1, C sub 1 a sub 1, plus C sub 2 a sub 2 equals B. That's what I'm rooting for. That's what I want to have happen. So from that, I would say C sub 1, because that's my unknown, 1, negative 2, negative 5, plus C sub 2, 2, 5, 6, is going to be equal to 7, 4, negative 3. Now, if I wanted to, I could actually multiply this all out. If I were to do that, I would end up with a system of equations, 3 equations and 3 variables. But I would be going in a big old circle, and I don't want to do that. Right? I'll just talk you through what I'm not going to write down, and then tell you why I'm not going to write it down. So I would get C sub 1 plus 2C sub 2 equals 7. All right, C sub 1 plus 2C sub 2 equals 7. That's kind of like x plus 2y equals 7. Then I would get negative 2C sub 1 plus 5C sub 2 equals 4. That's kind of like negative 2x plus 5y equals 4, and so on. I get a third equation. So you think about what have we done when we had a system of equations? We stripped it down to the coefficients, we row reduced, and then we came up with a solution once we got it into reduced row echelon form. So the big question would be, why would I distribute this all out? Why would I apply the scalars to write it as 3 separate linear equations just to pull out the coefficients when I have them right here? All right? So the idea behind this would be, let's just drop this down into matrix form. All right, so like I said before, we were practicing the skills involved in row reduction techniques. So now what we're going to do is, okay, we got those techniques somewhat down, but we don't want to get bogged down with those techniques. So what's going to happen is you're going to follow those techniques only when you're required to. All right, so what that means is that if I don't tell you to do it by hand, you don't have to do it by hand. All right, hugely important, because that's another reason why a person might take 3 hours on a test that should only take about an hour or so. All right, so this is telling you to whip out the old calculator. Back on, because now I have it. Pretty sure it works the same way on the app. I'm going to sit down from now on. My back is killing me again. So, matrix, menu, edit, matrix A. Oh, it doesn't work the same way. Oh, maybe it does. Let me see. 3 by 3. Okay, it does work the same way. One, 2, 7, negative 5, 2, 5, 4. Okay. So, second, hit the wrong thing. Matrix. So math, reduced row echelon form on matrix A. And we get that, barring any catastrophic miscalculation on my part. Yeah, I'm having a love-hate relationship with this app, the calculator app, because it does almost everything that the handheld calculators do in almost the same way, but it's different enough that I can't just say, all right, everybody, forget buying calculators, let's just use this app from now on. So it's not quite there yet, 1 year. But it's good enough for a display, so I guess it's $5 well spent by my school district. So anyway, we have a solution here. We just have to pull the meaning from this solution. And the reality is that it's not always the easiest thing in the world to discern, especially since we didn't go through the process of defining 3 separate linear equations. So you're like, possibly, oh, what could the 3 and 2 possibly represent? But really, if you think about it, there's only 2 possible candidates. It's just a question of, well, which one's the 3 and which one's the 2? Well, the C1 comes first, the C2 comes second. If I were to distribute this out, that's the order of the coefficients or the order of the variables within those linear equations. So we can, I think, with a reasonable amount of confidence, conclude that C1 is going to be equal to 3 and C2 is going to be equal to 2. And you could just do a quick eyeball estimate here and just run it through and see. If this is 3, if C is equal to 3, and C1 is equal to 3 and C2 is equal to 2, will that give us a 7 for the first computation? 3 times 1 plus 2 times 2. 7, right? Then you maybe try it for another one. You don't have to do it for every, especially if it's a vector, a column vector that's got like 10 entries in it. You don't want to do it for every one of them. That kind of defeats the purpose of a check. Do it for a couple of them. One, just, get the one out of the way, then maybe do a second one to make sure that maybe you didn't just get lucky on the first one. All right, so 3 times negative 2 is negative 6, plus 2 times 5 is 10, negative 6 plus 5, negative 6 plus 10 is a positive 4. So pretty confident. If you're sitting there taking a test and you got a lot of time on your hands and nothing better to do than check your work, then by all means check them all, but I wouldn't say that it's absolutely necessary. All right.
Is it ever the case that coincidentally all of them could work out except for the last one?
I've never experienced that, but I would imagine that there's like 1 in 10,000, there's that one case, and if you're gonna find it, you know it's gonna be on a test that you're gonna find it, so I guess worst case scenario, check them all. So then the next example is really just kind of talking about the same thing. In the previous one, determine whether B can be written as a linear combination of A sub 1 and A sub 2. Is the vector 4, 5, 5 a linear combination of the vectors below? It's the same question. All right. So that gets a big old star for me. so that you can do that one on your own. The big issue there. All right. So the question is the vector 4, 5, 5 a linear combination of the vectors below? And really, again, just to clarify, or not even clarify, just because I think I did a wonderful job of explaining it. No, it's really a question of, like, last time I saw you, it was Thursday, so maybe some things kind of slipped away. What we're looking for is some set of scalars that, when multiplied by these vectors, will give the vectors v1, v2, v3 will give us the given vector. All right. So the one thing that I would hope is that you'd never lose sight of that, because what happens is, and you'll find this occurs very frequently in this course, preamble, conversation, rationale, I talk, I hand wave, I tell you why it's important, why you should be interested in it, and how useful it's going to be, and then we create a matrix and we put it in reduced row echelon form and circle our answer. And it's like, oh, it's the same thing, right? And you'll find that that's a recurring theme, and it's not without merit. It's just that it's a technique that you're using for different purposes. I equate it to algebra. All right, you factor in Calc 1, Calc 2, Calc 3. You factored in pre-calc. You factored in algebra class. You didn't always do it for the same reason. All right, it's the same idea. So our ref is our factoring. All right, that's how important it is to this course. All right, so I'm going to define my linear combination as C1 V1 plus C2 V2 plus C3 V3, and all of that should end up being equal to V. All right. So it's kind of like the sum of three simple linear equations, like y equals mx. Forget the plus b. It's going through the origin, right? Because vectors are pinned at the origin, so we don't have to worry about a y-intercept, right? So we have the mx, like the mx part of mx plus b, for the first vector, then for the second vector, then for the third vector. These form the basis of our linear system, and so the question would be, is there a way that I could get to the vector something 5, 5, I can't see it, but it doesn't matter, 4, 5, 5, using these base vectors, all right? So C1, 1, 2, 3, plus C2, negative 1, 1, 4, plus C3, 3, 3, 2, and then all of that should be equal to 4, 5, 5. Now, I did some hand waving over this, or related to this last time. I do want to show you at least once, well, exactly once, because it's a step that you're not going to want to do more than the one time. But I do want to show you the one time how this all kind of equates to reduced row echelon form. So if I were to run through using the distributive property, scalar multiple, the C1 multiplied by V1, and then C2 multiplied by V2 and C3 multiplied by V3 equals 4, multiplying only by corresponding parts, I would get three separate linear equations. One would be C1 minus C2 plus 3C3 equals 4. So we're just multiplying through with the actual scalars. All right, then 2C2 plus, I'm sorry, 2C1. Jeez Louise. Was it a Monday? No, it's not. No excuses. Plus C2 plus 3C3 equals 5. 3c1 plus 4c2 plus 2c3 equals 5. All right, so if we think back to before we even started talking about linear combinations, we were talking about solving systems of equations. From that system, I said, I don't think I phrased it as a promise, but in my mind it was a promise that for now we're just going to take the coefficients, we're going to write matrices out of these, but later on I'll tell you why. All right, so what we did was we just simply took the coefficients that we saw here, 1, 2, 3, negative 1, 1, 4, 3, 3, 2, and 4, 5, 5, making the augmented matrix. So we had the coefficient matrix, and then the 4, 5, 5 makes the augmented matrix. And then we'd work off of that. All right? But previously, we never had this stuff. We never had the linear combination form. So we were given the equations just as linear in linear form. So we were just saying, okay, we'll just pull out the coefficients and do the RF to it. All right? Really, what we were doing is in each case, just behind the scenes, we were factoring out from this set of coefficients, we were factoring out a C1. From this set of coefficients, we were factoring out a C2. And from this set of coefficients, we were factoring out a C3. And indirectly, we were coming up with the linear combination form to then make the adjustment back to matrix form. All right? It's just we didn't show this step. And the reason behind that was it wouldn't have made sense. Back then, I mean, it's so long ago now, like a week and a half. If I were to say, okay, factor out a C1, be like, what the hell are you talking about? There are 3 separate equations. How do you factor out a C1? That's not how it works. But really, if you think of this as a column vector with a common C1, factor it out as a scalar, then it makes more sense. All right. So what we're doing now is we're actually skipping the part where it becomes a linear set of equations and just working with the linear combination. All right. And so this gets converted over into reduced row echelon form. And again, you know, you practice the skill with the hope that eventually you're not going to have to show all the steps every single time. And so here we are. That's this moment. Get this piece of garbage out of the way. That's the Microsoft Surface, in case there's someone at home wondering what I am talking about. And this can go down here. This can go up here. This, I suppose, I can resize just a smidge. Maybe bring it up, get it in. And now we have a nice juicy glare to work with. That's just great. I can't win. Oh, I'll kill a light, I guess. And there it is. Now it'll refocus like for 10 or 15 seconds and it'll be good. All right. So I do want to, oh yeah, every time I touch it, it's going to refocus. I'll try not to touch it. All right, so again, second inverse, edit, 3 by 4, 1, negative 1, 3, 4, 2, 1, 3, 5, 3, 3, 4, 2, 5. The moment during the semester when you think to yourself, dang, I gotta type another matrix in, that's the moment where you have officially become spoiled. And so at that moment, send me a message on Remind, just to let me know. Because I'd like to keep track of when that happens. It happens for different people at different times. Because you remember like the bunch of problems we did where we were doing the row reduction step by step with the serpentine technique, and it took like half an hour for each problem? like, we're not doing that, but eventually you'll get to a point where you will have typed in so many matrices where you'll be like, this sucks, I can't believe I have to type another one in. That you'll be far enough away from having to actually row reduce by hand that you will have gotten spoiled by this technique. So send me the message on Remind, something as simple as spoiled, or it happened, or something like that. I'll know what it means. Or I won't, and then we could have an awkward conversation about it happened. Oh, what happened? So, second inverse, go to math, RF, second inverse, we're in the matrix menu again. Really, again, just working left to right in that menu. Edit first, then math, then identify the matrix. RF, you get this. And there we go. Oh. All right, well, that's good enough, I guess. I was just going to snap a pic of it, but, you know, that's good enough. All right, so we could see that we have a row of all zeros. So it's not an issue, but it's something to be aware of. So what I'm going to do is address what my final answer is going to be. All right. So again, we have our three variables here, which are the scalars. We were solving for three unknown scalars, so they're taking on the form of variables. So we have C1. So I'm going to write it in the long form first. I know it can be kind of a pain to do that, but at least for this one time, let's just do it. All right, so I'll write it over here. C1 plus 2C3 equals 3. All right. And then I'll leave a little space below because I want to manipulate it algebraically. And then I would say C2 minus C3 equals -1. And then we have the row of all zeros. All right. So for that one, we're assuming that, well, there's no assuming. It really is 0C1 plus 0C2 plus 0C3 equals 0. But that simplifies down significantly. But let's address everything else first. I said I was going to leave room, and then I didn't. I don't know. Welcome to my world. I'm just going to write it all again. All right, so for my first equation, I'm going to solve for C1. So C1 is equal to 3 minus 2C3. For my second one, C2, we're going to solve for each variable. So C2 is equal to -1 plus just a clean C3. And then for the last one, we have this thing. It's an equation. It's a true equation because 0 equals 0, but everything's zeroed out, so it doesn't seem to be really telling us anything. But what it's really saying is no matter what I put in for C1, C2, and C3, I'm going to satisfy this equation. Well, I have a relationship between C1 and C3 in my first equation. I have a relationship between C2 and C3 in my second equation. The issue is I don't have a relationship, at least an obvious one, between C3 and C3. All right? Because this relationship tells me that just for this one equation, any of the constants, the scalar multiples, they could be anything. Any of them could be anything. So pick a number and it's going to work for this equation, but it's not true for the other equations. All right? C1 and C2 are strictly dependent on whatever C3 is. So in this case, if I'm defining what C3 is, I'm just going to simply make the statement that C3 is a free variable, but the mathematical notational way of saying that would be to say that C3 is equal to itself. All right, same as C3 is a free variable. All right, it allows C3 to be anything.
You say it's also like consistent and independent variable, or no?
You could get into that, but really you're just taking something that's really simple and making it more complicated by getting the words involved. I would say don't even bother with that, just go with C3 equals C3. Okay.
And you would like us to write down the test like that it's a free variable.
Not even that.
Oh, not even.
Yeah, once you say it, I mean, I'll accept that C3 is a free variable because it's a true statement, but the better way of writing it is that C3 is equal to C3.
Okay.
All right? Because that's notation-wise, and the notation. Honestly, I mean, if you're thinking like mathematically, strictly getting to the point, you know, like not using flowery language and fluffing up everything, like the simplest way to explain something mathematically is with a mathematical sentence. C3 equals C3. It's telling the whole story. All right? It's when you start getting words involved, that's when people start getting in trouble. All right? So anytime you could save yourself from that, it's probably a good idea. All right? So I can rewrite this as C1, C2, C3 as a column vector is equal to, I have all of my coefficients really, and I can even write this one, the C3. I could write that as 0 plus C3. All right, it's the same thing, because if every one of them has a structure of coefficient plus or minus something multiplied by C, C3, then we would want that to have the same structure too. So I could write this as 3, and that would address, get yellow in here, that's a better yellow. This bad boy right there. You got the -1 for that one, and then the 0. So we're looking at, again, 3, -1, 0, plus C3 multiplied by a column vector associated with the coefficients of C. So -1, I'm sorry, -2, 1, 0. And then you could actually just verify that this is equivalent to that, because I can just run through. C1 equals 3 plus C3 times -2, or C1 equals 3 minus 2 C3. All right? C2 equals -1 plus C3, boom. And then C3 equals, everything zeroes out there. Oh, sorry, that should be a 1, my bad. Hence the check. Which is ironic because I never check my work. So there's one time, I mean, I never use the word ironic correctly either, so I don't know. Yeah, this one time I was like, yeah, let's check our work, and that's the one time I made mistakes. One of them. So this is the parametric form of your linear relation, and you know, whatever it's called, it doesn't matter. It's just, it's a nice, concise way of writing your final answer. I mean, otherwise you have disjointed equations all over the place. All right. Parametric is just, I mean, if you don't have experience with Calc, and I say Calc 3, but it's really a pre-Calc topic, parametric equations. It's really just defining variables in terms of another variable. All right, that's what parametrics are. You're defining it in terms of a new parameter. So typically it's like you have an x and y equation, so you define it in terms of a new variable like t or s or something like that. So here we're defining C1, C2, and C3 in terms of C3. All right, so this is my parameter. All right, so all that means is if I know what C3 is, then I know what these values are. All right, and so it's clean, it's nice, we like this. Well, maybe not the first day, second day, but eventually we come to love it. So that's our row reduced matrix. And now we just have to do something with it. Now it is asking for a linear combination, so we do need a little bit of the setup, but the setup's simple. It's the same every time. You know, sometimes they'll vary it. I mean, it's vector v here, so we're good with the v1, v2, v3, but they could say vector w. All right, so if that's the case, then you adjust accordingly. But we're looking at c1 v1 plus c2 v2 plus c3 v3 equals v. That's our linear combination. All right, and so from that we're getting, now this one's really nice because you would include this. Can I actually edit? I never tried this before. Oh, that's something. Okay, you learn something new every day. You get this in your row reduced form, assuming I typed it in all correctly, and you can see that it's a very clear C1, 2, and 3 does not need to be defined parametrically because they're very clearly 2, 4, and 1. So this is not going to be an open set. This is a singular solution. There's only this one way that you can get from those vectors, the v1, v2, v3, those column vectors, to the desired vector v. That it's only happening this way. The previous problem that we did, there's infinitely many ways that it could happen, all dependent on what you choose as your C3. All right. Here it has to be this, which it's kind of nice because it's nice to have a single answer as opposed to infinitely many. But the thing is, gone are the days when in an algebra class you could just say there are infinitely many answers. I want to know in what capacity you have infinitely many answers. Tell me what kind of infinite. That's what the previous question was talking about. This one is finite, it's a single value, or the single vector. Okay. This one you might actually like. Is the vector a linear combination of the other vectors? I like those kind of questions. So it's still the same setup, but now we're looking to see if a solution exists in any way, shape, or form. So I don't really need to get to a point where I'm stating a solution as much as I have to just analyze my row reduced form and make a statement of whether it leads to a solution or not. All right. So again, C1 V1 plus C2 V2 plus C3 V3 is equal to V. And now we got a big old question mark here because we're not sure. So 1, 2, 3, -1, -1, -2, 1, 4, 5, and then the augmenting column, that bad boy right meow. And then let's get my calculator. Gigantic screen made tiny. And that's on low. You can do that. So edit, dimensions are the same, type it in, 1, -1, 1, 3, 2, -1, 4, -4. Name of the game is typing it in correctly. Because again, once you get a hand, I mean, as tedious as a lot of this stuff is, there is satisfaction in knowing that once you get to the setup, you know what to do after that. The process is virtually the same in every case, to the point where I'm just going into my home screen and hitting second enter because it's still matrix A, and I'm still looking for the row reduced form. Aha, look at that. So let me bring it in a smidge. Yeah, look at that bad boy right here. Ooh. Yeah, you got that pivot there. Pivot in the last column. Therefore, no solution. Cannot be written as a linear combination. Cannot be written as a linear combination. All right. Once you come up with a no solution, there is no set of scalars that could satisfy this linear combination equation. Pivot is the first non-zero entry in any row, or any row. So once you identify that first non-zero entry, like in the first row it's a 1, second row it's also a 1. In the third row, the first non-zero entry happens in the last column. That's your pivot value. If that pivot happens in the last column, that means there's no solution, because you end up with a contradiction. So what this would equate to in equation form would be 0C1 plus 0C2 plus 0C3 equals 1. Simplify it down, 0 equals 1. Contradiction. All right? Anytime you have a contradiction, it would imply no solution. One question on there, on that tech assignment, it's really just asking, when that vector shoots out into space, where's it going? All right? If a vector spans all of real space, it must touch every aspect of that reality. All right? So if it's 2 space, then that vector has to hit every little tiny square inch of that real space, that 2 space. Now, obviously, you start increasing the dimensions, you're going to make things more complicated, all right? So you have a vector that's coming out of this corner here, shooting out into space, and I'm telling you, here's our 3 space. That vector, and you use a broom or something, that vector has to touch every cubic inch of space in this room. All right, so it's got to hit every atom that exists in the volume contained in this room. All right, how do you prove that? All right, well, fortunately, we don't have to go atom by atom. We could, if we know the basis of reality, so this is the basis of our system, then we can use our row reduction techniques to make a determination of whether or not you will have a real solution. Because that's the whole thing. I don't need to know what the solution is. I just need to know that a solution exists. All right. So what I need to know in this example here, this really kind of spells it out in 3 space. When I say does S span all of R3, all of real space in 3 dimensions, I'm really just asking, can ABC be written as a linear combination of the basis of that 3 space? All right. So we're basically going to do the same thing we just did. So I'm looking at some arbitrary constants. And I'm going to call C1 C2 and C3, spoiler. Hi, can I help you? This is not.
Do you know this?
I honestly have no idea. I'm sorry. I wish I did, because I don't. Somewhere in this building, there is a statistics course that's being taught. I hope she finds it. Anyway, so this is what we're looking at. We need to prove the existence of a solution. All right. So we go right on down to our augmented matrix. Now, I throw that little nugget at you a few minutes ago saying you could use your calculator unless you're told otherwise. Sometimes you're indirectly told otherwise. Oh, you put an A, B, and C in the calculator. You're not. All right. So we're gonna have to work this through, but we can handle it. All right. I'm gonna take you through this. I'm not gonna spoil the conclusion. It's just I don't want to give away what we're looking for until it happens or doesn't happen. All right. So we're gonna start row reducing and see what happens. All right. So again, all the different things are in play. You could swap rows, you can multiply by a scalar, or you can use the technique of multiplying and adding. All right. So it looks like I can wipe out both the leading entries in rows 2 and 3 off the bat. So I'll do that first. I'm going to do a -2 R1 plus R2. Simultaneously, I'm going to do a -R1 plus R3. So we're leaving row 1 alone. So the first entry is going to be 0, because that was the whole point. Second entry will be -2. Then we'll have a -1. Fourth entry, a little bit of a different story. It's going to get ugly. Ugly's okay, though.
B minus 2a.
Yeah, B minus 2a. Ugly's okay as long as it exists. All right, because we're proving the existence, not anything in particular. We just need to know that there is a solution. All right. So then, last row, 0, 1, -1, C minus A. All right. So, first column, check. Second column, now I want to, again, ideally we get the identity matrix for the 3 by 3, but if not, at a minimum, I want to make sure I have the zeros below all the pivots to get it into echelon form, and then zeros everywhere except for the pivots to get it in reduced echelon form. Right, so I can now start thinking about manipulating some of the other rows. Right, so here, I guess I could try to take care of that -2, but then I'm gonna incorporate fractions. I don't know if I'm in love with that idea. Okay. I can negate row 3 and add it to row 1. If I do that, that's gonna get rid of the first entry. It'll make the second entry, it'll make the third entry a little bit more complicated, but at least it'll make that second entry go away, so that's something. The other thing that we can do is have in mind, and so people often forget that swapping rows is a thing. I don't like this as my middle row. I can swap it with the bottom row because that's a little bit more convenient. But what I can do before that is I can kill that -2 and then do the swap. Or do the swap and then kill the -2. It really doesn't make a difference. All right. To make it as not complicated as possible, if that's a correct grammatical way of saying anything, I'm just going to do the swap first. So 1, 1, 1, A, 0, 1, -1, C minus A, and then 0, -2, -1, B minus 2A. So then what I'll do is 2 times R2 plus R3. So the first 2 rows are going to stay put. 1, 1, 1, 1, 1, 1, 1, A, 0, 1, -1, C minus A. The third row is the one that's going to get manipulated. All right, so we're looking at 0, 0. If I take 2, multiply it by -1, I'm going to get a -2, plus the -1 that's already there is going to become a -3. Then algebraically becomes a kind of thing. So 2 times row 2, so 2 times C minus A plus B minus 2A. Simplify if you want, simplify if you need to, or don't. It's up to you. Because again, we're looking to show existence of real numbers. So, what does that mean? No undefined, no imaginary. All right? If we avoid undefined and imaginary, then we're accomplishing the goal. All right? At least as far as the numbers are concerned. We also have to be careful about pivots, because if the first pivot value is in the last column, then we got a problem. All right? Because that would imply that there's no solution. All right? So if this 3 goes away, this -3 goes away, but we have a value in this last row here, then all bets are off. All right, I'll talk more about that next class. All right. But in my next move, it seems like I'm probably going to want to divide that last row by a -3. So maybe simplifying is the way to go. So I'm just going to do it off on the side here. 2C minus 2A plus B minus 2A, which all simplifies down to 2C minus 4A plus B. Any order you want, it doesn't really matter. All right, just make sure if you move things around, bring the signs with them, obviously, but aside from that, it's okay. Let's see. Yeah, I think our next move is to divide by 3. So 1/3 of row 3. So just all that stuff over 3. So that's something. I mean, it's a lot to write, but at least it's not stuff you have to think about. Oh, sorry, negative 1/3. Because we want it to be a positive 1. All right, so I'm going to put it over a negative 3 because I don't want to have to worry about distributing the sign, aka I forgot. So I don't want to have to erase everything I just wrote. All right, we can actually wipe out the negative 1 in row 2 now by adding row 3 and row 2, which is one of those things where you're like, that was the one thing I was hoping I wouldn't have to do. But that's what needs to happen, so, or it's one of the things that needs to happen. Row 3 plus row 2. So 0, 1, 0, all that stuff added together. Again, I'm not simplifying unless I have a dang good reason to. So C minus A, I can write, instead of plus, I can write minus, and then the whole fraction, 2C minus 4A plus B all over 3. And then the bottom is going to be what it was, 0, 0, 1, and then all that stuff again. Here I think I might just negate the numerator just to clean it up a little bit. So 4A minus B minus 2C all over 3. All right, eventually we're going to have to do something with row 2 because I want to use that on row 1 to get rid of that middle entry. So it's going to happen. It's just a question of do I want to clean it up now or do I want to clean it up later? It's kind of up to you. But on the side we could just do the work to clean it up and then just leave it in the matrix the way it is. So with a common denominator, I'd be looking at 3C minus 3A minus parentheses 2C minus 4A plus B all over 3. So we'll have a C. Negative 3 plus 4 is A, so plus A. And then minus B over 3. Which is actually, I don't want to say shockingly simple in comparison, but it's definitely simpler. All right, so when we go through the process of working this against that, it'll be a little bit easier. So that's something. Little side work. So, but what I wanted to do is my next step, and you might disagree, you might want to do something different, and that's up to you, but my thinking has me working with row 3 on row 1. So negative row 3 plus row 1. So second row is going to remain unchanged, but I'll write my new expression in there. I'll write it as A minus B plus C. Over 3. And then 0, 0, 1. And then 4A minus B minus 2c all over 3. So then I just got to work row 1. If I'm negating row 3 and adding to row 1, it's going to be 1, 1, 0. Now this whole thing is getting added to A. All right. You could do that some on the fly, I think, because I can actually just manipulate the A right now and just call that 3A over 3. Because I would need a common denominator. So if I'm going to add these two together, negative B and C are going to remain the same. I'm just going to take the 3A and add it to the A that's already there. So it's going to be this same fraction. Oh, sorry, I was looking at the wrong thing. You're going to have the negative B and the negative 2C are going to remain the same. So I'm just adding the 4A and the 3A. So it's going to be this same fraction, just instead of the 4A, it'll be a 7A. All right. So little things like that can make a big difference. And then the last step has us, and by the way, we know we're still in good shape because my denominator is only a constant 3. There's no variable in the denominator. So I don't have to worry about any circumstance in which this is going to be undefined. All right? And it's also looking like we're going to get the identity matrix. So as long as we can avoid a variable in the denominator of the fraction, we're going to be golden. We're not going to be looking at any instance in which this would fail. All right? And we'll have a legitimate proof. So the last thing that we need to do is negate row 2 and add it to row 1. So negative R2 plus R1.
Could you negate row 3, the ABC before adding to A?
Schnitzengruben.
Yeah, so it should be 1A.
It should be 1A and then plus, right?
Plus B
Plus B plus C. Thank you. Then, of course, there's that, like calculations and stuff. Good.
Doesn't it show? Minus A.
I have a negative 1/3 on the outside, then A plus B plus 2C.
So you have a negative.
Yeah.
It's a negative A, right? Because it's 3A minus 4A.
3A minus 4A, so negative, yeah. And then it's negative this whole thing.
Be a negative A minus B minus 2C. Or you factor out the
Right.
negative and put it on the outside. And then it's positive.
So we negated this, so that changed all these signs. Then we added the 3A, so
Negative 1/3.
Negative A plus B plus
N-
2C.
So negative A, then plus, then plus, right?
Yeah.
Okay. Okay. Now we got it. Okay. So then the last move, negate row 2 and add it to row 1. So we're looking at the identity matrix, so that's fine. And so we really only have one challenge ahead of us to make sure I don't screw up this next part. All right, so I know it's going to have the common denominator, so that's the the one good byproduct here, we're negating and adding. So if I negate this and add it to that, negative 2a, negate this, it becomes positive b, plus b becomes 2b. Negate this, add it to that, negative 1 plus 2 becomes 1, so 1c, so plus c. So the solution exists. Therefore, S spans the set of all real numbers in 3 dimensions. That's a lot. Look at that. All right, and again, all we were looking for was existence. All right, so C1 is equal to that, whatever that is. If you knew what A, B, and C were, then you would know what that is. C2 equals that, C3 equals that. All right, so we now have, well, we already knew the basis for this reality. These solutions give us the formula to navigate that reality.
What would like a non-solution look like? What would it look like if it like weren't to span that thing?
You would get all zeros here and then a value in that last column.
Okay.
Because what you end up with is a contradiction somewhere. Anywhere that there's a contradiction means that there's no solution.
But what if it's like all zeros?
If it's all zeros, then that's fine. Yeah.
Okay.
So yeah, so all you're worried about whenever you're row reducing is making sure that you don't get a pivot value in the last column. All right, if there's a pivot value anywhere except for the last column, you're good. But if that first non-zero entry in any row, if that first non-zero entry hits in the last column, no solution. All right. So yeah, it's the terminology sometimes more than anything else, but that's really the long and short. Thank you. All right, so write W, X, Y, and Z as linear combinations of U and B. That would be separately, as separate equations. So a linear combination in this context, it's really amounting to the same thing, except the vectors are represented visually and not numerically. So you don't have column vectors to work off of. But you can still use the same idea of scalar multiplied by vector, and maybe plus another scalar multiplied by another vector to get you where you want to go. All right. This is a great problem. I honestly thought when I first came across this problem, I'm like, okay, busy work. Like it's just a problem that somebody invented because they needed to kill like 10 minutes of class time or something. I don't know. But when I actually started using problems like this, they ended up being the most valuable because this is a great visual representation of the concepts associated with a linear combination, right? So if you didn't understand it in the numerical form, this is going to clarify a lot of things, all right? So I have, I'm just going to start off with one of them. I'll go with vector, well, W. All this is saying is I'm starting at the origin and I want to get to vector W. Find a path that'll get you there. But that path needs to be in terms of simply just U and V. All right. Now, spoiler. Oh man, I hate when I do this because then, all right, this is what I do. It's like my biggest failing in life, math teacher life, is I make these promises in class and it's hit or miss as to whether or not I actually fulfill them. So what I was about to say is, spoiler, I'm going to put this exact same picture on the test, just ask you maybe instead of using U and V to use A and D, or B and C, or X and Y. But now I'm worried I'm going to forget to do that. I could just make a note to myself. All right, let me put it on my list of things to do. All right, so I'm committing to it. It's going to happen. You don't know whether or not this is good news because I haven't done over it yet. It's good news. There's some things you just gotta kind of believe me on. What page is this?
14.
Page 14. Pick on top. Put it on test. And I promise I'm not going to try to find a way to make it the hardest question in the world or anything like that. Every test I always throw what I think is a gimme. If you follow along here, then here's your gimme. All right. So I need to get from the origin to W just using U's and V's, and in any capacity. All right. So pick a pathway and see if you can use a pathway that's strictly in terms of U's and V's. All right. So I got one here. That's one. I got one here. Oh, cannot draw a line sufficiently. And I got one here. Well, if that's a whole pathway, I think we'll agree on that. If I go down this way, then shoot up that way, we can get to W that way. All right. So now I just got to think about what I did. All right. So this pathway here. Well, U is here, going in that direction. Negate U, we're going in that direction. So it's on the same line going in the opposite direction. It's labeled here as negative U, so it makes it even easier. So I know that I have one part of it that's negative U. All right. So W is equal to negative U. And then each one of these segments is a V. So if I were to go two of those segments, I'd have 2V. But that also happens to be labeled. Right here, this point is 2V. Opposite sides of a parallelogram are congruent. So I know that this is also going to be 2V. Right, still in the positive direction. Right, once we define this as the positive direction, the other way is the negative direction. All right, so I'm looking at U, negative U plus 2V. All right, so you just take a look at this. This is the same idea as C1 V1 plus C2 V2 equals V. All right, it's just in this case we have a W, we have a negative 1, a U, a 2, and a V. Same structure though. All right, so this is really a common sense explanation to the idea of a linear combination. All right, so if I'm taking vectors in space, it's really just saying I got these two vectors to work with and I got to get to this point over here. How can I do that? Well, I can go 3 of those and then 3 of those. So 3 of these and 3 of those, add them together and I get the vector that I want. All right, so 3U plus 3V, or 3W plus 3 whatever, doesn't matter. All right, so this is that justification, but it really does a great job of explaining visually what a linear combination is talking about without getting bogged down in all the matrix operations. All right, so the second one is to figure out a way to get to X from the origin, always from the origin. So I can take 2 steps along that U line in the negative direction, so negative 2U, and then 2 steps along the V line in the positive direction. Then I got to get to Y. I think that's an easier challenge because I'm getting from the origin to the point at Y. Well, I got to go through X in order to get there, right? So y, in order to get there, I have to do everything I did to get to x, and then a little bit more. So the negative 2u is in play, but this time I have to go 4. What are we looking at? That's a half unit, right? So 1, 2, 3.5. So 3.5v.
Could you write y equals x plus 3.5b?
You,
Plus 1.5.
Yeah. but
I
it's
would
the same.
say under normal circumstances, yes, except these directions say specifically as a linear combination of u and v. So just to satisfy the directions, you'd have to write it that way. All right, so last up is z. All right, now it got cut off, and that's okay, but you could assume that the trend is still going to be the same. So there's no reason to think that the trend, they're parallel lines. There's no reason to think there's going to be any change. So that's telling me I'm going to take 3 steps in the negative u direction. And then 1, 2, 3, 4 steps in the positive v direction. Unless it's not. But I think I would have felt terrible if I skipped that problem, because that helps get the visual sense of what's going on. I mean, that's a good question. All right, so matrix equation AX equals B. Yeah, it's a great equation. We'll get to it, but for now we're gonna address the concept of matrix multiplication, just because that goes into it. I mean, the idea is if you have an equation AX equals B, you're multiplying 2 things. It's just a question of what those 2 things are. All right. So A is the m by n matrix. So any dimensional matrix, right? Not necessarily a square matrix. So it could be a 19 by 20 matrix, which would be a calculator problem, right? You never have to do that by hand. X is talking about a column vector of some capacity. You know, it could be 2 units long, or it could be 30 units long. All right. So we're learning how to multiply these 2 things and then set equal to some other column vector. All right. So how do you actually multiply? Well, there's different ways of handling it, and really it's every time I do it one way, people want me to do it the other way. So like I can't win. So I'm just going to do it the way I like to do it, and that's going to be the end of it. All right? But the technique is fairly simple. I mean, it's based off of this idea. AX equals a sub 1, a sub 2, all the way up to a sub n, and then multiplied by x sub 1, x sub 2, all the way up to x sub n. It's going to give you this linear combinations kind of tying together. It's kind of funny how that works. So if you have a single row of a matrix multiplied by a column vector, you're just taking the first entry in your row and multiplying it by the first entry in your column, taking note of what that gives. Then the second entry in your row multiplied by the second entry in your column, taking note of what that is, and so on all the way down to the last entry in your row and the last entry in your column. And once you get all that, you're going to add it all up. All right? So if you know anything about a dot product, this is going to feel very similar to that. All right? And in fact, this is really just, well, it is the dot product. In reality, this component of it is a dot product. It's just we're orienting this row in a different way than one would do it if they use a dot product. If you never heard about a dot product yet, ever, then don't worry about it, because we're going to cover it in this class anyway. All right. So what that's telling me is that I'm going to take every entry really in the first matrix and multiply it by every entry in the vector. All right, so it sounds like fun is really what I'm gonna. And then you do the same thing with the second. All right, so I'm gonna do 1 times 5, 5. 4 times 0, 0. -1 times 2, -2. And then I'm going to add those three bad boys together. This is, let me just kill it that way. My nightly robocall. Then the missed call alert, and then the voicemail that's a second and a half long with just static, and then around 11:55 tomorrow morning I'll get another one, then 3:30 I'll get another one, then this time again tomorrow night I'll get another one. So I'm 3 robocalls a day. That's what I'm up to. What a world. So universe now. So 3 times 5, 15. 1 times 0, 0. I almost said 1, which would have been actually one of the more common mistakes when it comes to this sort of stuff. The number of people that multiply by 0 and don't come up with 0 would shock you. Like, it happens all the time. It's just you get in a groove and you start doing the calculations and just something goes haywire. Got a little extravagant tail on my 2 there, so let me dial that back a little bit. No need for such enthusiasm. So then 17. All right, so I have these 2 values. But then the question would be, okay, are these 2 values floating in space, or what are we looking at? Well, there's an easy way to figure out how these 2 values should be represented in the final answer. So the original given matrix was a 2 by 3. The given vector was a 3 by 1. Always rows first, then columns. Rows by columns. All right? 2 by 3, 3 by 1. All right. So it's kind of along the lines of like logical rules of logic, I guess. So kind of painting myself in the corner. Like conditional statements and things along those lines. If this, then that. If that, then that. Therefore, if this, then that. So it's basically saying the result should be a 2 by 1. All right. So 2 gives a 3, 3 gives a 1, so therefore 2 gives a 1. It's a really kind of a hand-wavy sort of way of explaining it, but that's how it would work. So our final matrix should be a 2 by 1 matrix, so 2 rows, 1 column. So therefore our product is going to be 3, 17. So column vector 3, 17. All right. Now, you might say, well, okay, that's what I was going to write anyway because that's how it worked out. You only wrote that, it was only going to work out that way because I chose to write the work this way. I mean, if I wrote it next to one another, so here, and then put this work over here, it wouldn't necessarily stack up, so you wouldn't reason it out that way. Right? The only way matrix multiplication actually works is if the number of columns in the first matrix is equal to the number of rows in the second matrix. All right? And the rationale behind that is, I mean, here's a non-math explanation. Stuff ain't going to line up if it's any other way. All right? That's the reality of it. So when I want to take each of these 3 entries and multiply it by each of these 3 entries, there better be 3 entries across the first row and three entries across the column. Otherwise, you're not going to have corresponding parts. So if I were to actually swap these two, that would be a problem because I'd be like, well, I have a row with one entry. What am I multiplying it by? There's too much. All right, so it actually matters in what order you multiply things.
So I was looking at the proof for it in our textbook, and I think I popped the blood vessel. Do you actually understand it?
Yes.
The actual math notation proof?
Yeah, it does boggle the mind a little bit when you look at it, but the notation I think sometimes gets in the way of understanding.
Right, it's
when
really simple to understand if you think of it practically.
Yeah.
What you just did, but like I wanted to understand the math and
Yeah, that's kind of why I avoid it. Yeah, because it ends up being a little too bendy. But I mean, it's something that I can definitely take some time and kind of walk through at some point. So, because it's kind of worth looking into. But it's something. Yeah. Now, maybe we'll do that. See if we could do that maybe beginning part on Thursday. Yeah, that's probably going to be the best way to go. Because it takes a few minutes, but it's something, because at least connecting the notation to like the practical way of thinking about it, there is value in that. And so that's yeah, we'll do that. I'll commit to that. Again. Reply. Proof of matrix multiplication. So I just showed you how to do it by hand, and you could see like 2 rows, 1 column, not too crazy, the calculations. Throw in more rows, more columns, it gets crazier and crazier. So maybe there's a way you can do it in the calculator. I think there is. Yeah, you know there is. Of course there is. All right, so I'm going to put in matrix A, my 2 by 3 matrix, 1, 4, -1, 3, 1, 1. Then I'm going to quit out of there. Then I'm going to put in matrix B, the 3 by 1 matrix. I had selected matrix A again, that would have been a problem. Edit matrix B, a 3 by 1, which is 5, 0, 2. All right, you ready for some next level stuff? It's very complicated, a lot of keystrokes involved. You're gonna go into the matrix menu. You're gonna select option 1, which is matrix A. You're going to select the multiplication symbol. And then you're going to go back into it and select matrix B. And then you're going to hit enter. I feel like I sold that pretty well. All right. Now, this whole thing of 2 by 3, 3 by 1, giving a 2 by 1, well, cool. One less thing to worry about, right? It gave it as a 2 by 1 matrix. Also, the calculator won't let you screw this up. So if I select matrix B, so basically if I do it out of order, it's going to be like, what are you trying to do? Have you even been paying attention in class? That's what it's trying to tell you right here. It's saying dimension mismatch. And there's no other way to really explain what the problem is in what you try to type in. like, if you were to come up to me during a test and say, I got this error message on my calculator, can you tell me what I did wrong? I'm gonna say, I think you mismatched your dimensions. You should match them up. Because if you match them up, there won't be a mismatch and you'll get it right, all right? So if you hit go to, it doesn't really clarify things anymore than to say, there's something wrong with what you did here, but then again, maybe there's something wrong with what you typed in for the matrices to begin with. But like if you hadn't figured it out at this point, then I would question whether you know what the rules of engagement are here. So just some things to be careful about. But generally, if you get that error, it's like, yeah, I put it in backwards, let me put it in the right way, and hit enter again. Ah, there it is, I got the right answer this time. All right. The only time that you could get a little crossed up is when, you know, it's like you're dealing with matrices that maybe, no, actually no. Nope. I was trying to come up with an example of where you could still get the wrong answer, but like you get an answer because you put it in backwards, but you just won't get an answer. Because even if it's square matrices, like if it's two square matrices multiplied together, it doesn't matter which order you do it in, it's going to give you the same result. So yeah, it's either going to give you an error or it's going to give you the right answer, and that's the end of it. All right. So the difference in difficulty level between the first example and the second example, well, I suppose it depends on how you find typing matrices into your calculator. If you find it to be difficult, then number two, the second example might be crazy. 2 by 3 and then a 3 by 2, right? By hand, definitely more complicated, all right? Because 2 by 3, 3 by 2, you're gonna get a 2 by 2 matrix, which means that the 2 calculations I did here, double that, because you'll have to do 4 calculations, all right? So keep introducing rows and columns, and you're gonna keep introducing more work. But not for the calculator, you're just typing in more numbers, all right? So hopefully that kind of makes it a little less stressful when it comes to this sort of thing. And again, I'm not a big fan of getting bogged down on the simple calculations. Honestly, I feel like when I was a student, I never got to the fun part of linear algebra because I feel like we were like at midterms before we were done learning how to do row reduction because everything was by hand. And it's like, this sucks. So, like the cool stuff, like the visuals, that never really happened for me. It was sad. Speaking of midterms, just because I said the word, and I just want to make it ultra clear that that's not a thing in this class. All right, it's just 3-unit tests in the final. All right, so theorem. Anytime you see theorem in this packet, that's something that's really important. Highlight it.
Question. So I put in the calculator. So do I just write equals and then the result?
Yeah. Just give me the answer and move on. Yeah. Supporting details for simple matrix operations, not overly interested in it. That being said, from your perspective, you're doing one of two things when you're taking the test. You're either double, triple, and quadruple checking that you type that information into the matrix correctly, or you're showing supporting work so that on the off chance that you did not type it incorrectly, there's room for partial credit. All right, it's just, you don't want to throw away easy points. The equation AX equals B has a solution if and only if B is a linear combination of the columns of A. So kind of like what we were just doing, right? I mean, you're going to see the recurring theme over and over again, right? But we're moving towards dealing with different types of equations involving matrices. So this is where we start. So this is a matrix, a 3 by 3 matrix. We don't actually know what it's referencing, right? It's a subset of real space dimension 3, all right, so R3. We want to know, is U in the subset spanned by the columns of A? All right, so the columns of A represent vectors normally, all right, but a matrix can represent anything. Most visually, they represent vectors, but they could represent weights, you know, like for a grading system. Like if you have a 60% of your grade is tests and 20% is homework, another 20% is participation, whatever. Like those weights could be columns, but what's the point of graphing that? Like it's not going to really add anything to the situation. I mean, unless you really like that problem we did with the U's and the V's, where you could take those little waves and be like, oh, here's my little test vector, and you know, the quiz vector, and it's like, oh, I can inch my way all the way up. Like I got 30 of those test points, and I got 20 of those homework points, and that's my grade. And you could do it all visually, just moving little tiny vectors all over the place. All right, so you could be standing there in the library trying to figure out your grade that way. I promise you, it won't look weird, right? So that's a possibility, but visually, we have column vector 2, 0, 1, 5, 1, 2, negative 1, negative 1, 0. This is going to create a basis of a real system, all right? That basis will span outward throughout real space dimension 3. We just want to know, is it going to capture U, all right? Put it in GeoGebra. Put these 3 vectors in, just like in the tech assignment, create the span, and see if that vector falls in there, but you're not doing that on a test. So, or at least not until everybody has like smart devices and all that stuff. So, at this point, what do? We create an augmented matrix. All right. So, graphically, and I'm just gonna make note of this. Graphically, the columns represent vectors that form the basis of the real space in the third dimension, in 3 dimensions. All right, it's not necessarily going to represent all of 3 space. It could be what we call a subspace. All right, so it could just be part of the real space. All right, so because as you know, 3 dimensions go out as far as the eye can see. You could go out to X, Y, and you can go up. Anything that you can see is part of real space in dimension 3. This could just be some subset of that. Maybe you're only going up 45 degrees, for example, and you could your field of vision is only the space that you can see below the 45-degree mark above the XY plane, right? So that would be a subspace of the real space in R3, all right? So what we want to know is, was it U? Yeah. U fall in the subspace of R3 created by the vectors in matrix A. All right, but again, it's a lot of language. But I want to teach for understanding here because we already know. You create the augmented matrix, you put it in your calculator, you hit RF, you get an answer, and you write it down. I would really love if you could actually understand what it all means. All right, that's the idea. That's why I take my time with this stuff. And I yell at other people when they say that I'm going too slow and all that good stuff, because you know what? I'll go as fast as I want. The slow, you know, like I don't drag my feet with this stuff. I will teach for understanding because I actually care that you walk away having a sense of what all this stuff means. Because this, anybody can do. That takes some thinking.
So A is a plane, right?
A is, well, this is in 3 space, so a plane is just a 2-dimensional surface within 3 dimensions. So it's not necessarily a plane. If you actually think of it as a cube that expands outward, because a plane works to cover all of 2 space. Like if you had just one plane in 2 space, you'd cover everything. Now, if you had an infinite, not infinite in number of sides, but infinite in the length of side of a cube, then you would have covered all of 3 space. All right, because what happens is you're going out along X is, you know, as far as infinity and as far as negative infinity, you're going out in terms of Y the same way. So you have a square, that's your plane. But then once you incorporate the 3rd dimension, now you're lifting that plane upward and you're creating the cube. So imagine this floor, Star Wars style. The floor and the ceiling are pushing in on one another. All that space that it's covering, that volume, that is part of 3 space. All right, except it with walls, not floor and ceiling, as we all know. All right, so, but conceptually, I mean, that's the good conversation because, again, here we go. Second inverse, edit. 3 by 4, why? Because it's always a 3 by 4. 2, 5, negative 1, 4. 0, 1, negative 1, negative 1, 1, 2, 0, 4. So excited by this. I'll just keep hitting second enter till I find the one. If this is the only math class you're taking, odds are, in the history, you have a calculation that you could use pretty much for every problem. Just keep hitting the up arrow or second enter. You probably don't even have to find RF anymore. Now, one thing I do want you to be careful about, because it seems, based on the notes, that the questions that I've chosen for the notes, every time that I ask is, the answer seems to be no. That's not necessarily going to be the case on a test. All right? So, is U in the subset spanned by the columns of A? No. Pivots in the final column. All right? But it could be. It's just not in pretty much every problem I've gone over so far related to these kind of ideas. All right? So, no, because pivot is in the last column. Therefore, system has no solution. Yeah, that was the whole page. Okay. Let's see how far I want to go tonight. Yeah, this is probably going to be it. I'll just do this last example and then I'll give you the lay of the land and then we'll go from there. So A is an m by n matrix. U and V are vectors in Rn, so n dimensional space, and C is a scalar. Then we have these two properties, right? So the distributive property. So matrix A can be distributed through vectors U plus V. So the sum of two vectors, visually we learned about what that takes the form of graph, in the form of a graph. Last time, 2 classes ago, I think. And then also we have, it's a form of the commutative property, but basically it's telling us that we can essentially factor out the C scalar. The C can be pulled out or it can be put in to the product. So basically, if it's a constant multiple or a scalar multiple of vector U, I could multiply the two matrices first and then multiply a scalar on later on. So it's essentially the commutative property, but with 3 factors. All right, so the proof here, the first proof, and I'm going to let you try the second one on your own before I spoil that one for you. Neither of them are bad. We have A times U plus V, and we're working in 3 space. So A times U plus V is equal to AU plus AV. Now we're using matrix A as A1, A2, A3. Right? So just simply that. So that's kind of nice. We're not dealing with something that's crazy elaborate. Right? So all I'm going to do is on the left-hand side, I'm going to take matrix A, A1, A2, A3, and multiply that by vector U, which would be U1, U2, U3. I know it would have 3 entries because it's in 3 space, which would then be added to V1, V2, V3. So I'm just working the left-hand side. You could work the right-hand side if you want and make it correspond with the left-hand side. It's up to you. But, I'll just pick a side and start working. Now, we know that vector addition, I'm not talking about the graphical addition, just the act of adding 2 vectors is as simple as adding the corresponding parts. So we're looking at U1 plus V1, U2 plus V2, and U3 plus V3. All right, and so we have the A1, A2, A3 in the front. All right. And I'm going to preface what I'm about to do by saying there's a bunch of different ways to do this, some easier than others. My brain took me in this direction this time. If you look at videos from previous semesters, you might see 4 or 5 different semesters, 4 or 5 different approaches. All right, so there's really no wrong way as long as you're applying appropriate algebraic properties. All right, so by finding the addition here, I just made my life a little easier because matrix multiplication is just telling me to take the corresponding values and multiply them. So simplifying this is really just a matter of taking A1, multiplying it by U1 plus V1, plus, because this is a 1 by 3 and a 3 by 1, so the final result should be a 1 by 1. All right, because we're multiplying here, I'll just make a note of that. This is a 1 by 3, 3 by 1. So the result should be 1 by 1. So that serves two purposes for me anyway. Maybe you don't need to know that, but I like to know that for two reasons. One, to make sure that multiplication is a legitimate move at this point, because I can't make that move unless the number of columns is equal to the number of rows. And then also, it tells me what I should get as a final result. All right? It's just nice to know that.
So you just basically multiply
Essentially, yeah.
when it's not 3 is the same number.
Yeah, whatever the common value is, you're just ditching it. All right, so then we'd have A2, a couple straight marks there. U2 plus V2. And then A3 times U3 plus V3. Now this isn't a far cry, at least in terms of the mechanics, from the proof behind matrix multiplication to begin with, but there is an element to it where we address the rows and columns and why they are the way they are. So there's that part of the proof that we'll have to address on Thursday. But for now, we can just continue. Distributive property, A1 U1 plus A1 V1 plus A2 U2 plus A2 V2 plus A3 U3 plus A3 V3. Now, in the case of the red line here, the A's were the scalars, essentially, and the U's and V's were vectors. But we could kind of change the role of things and move things around so that all the U's are grouped together and all the and all of the V's are grouped together. So I'm going to write it as A1 U1 plus A2 U2 plus A3 U3. Then for the V's, A1 V1 plus A2 V2 plus A3 V3. All right, so we're actually almost there, because if you see the structure of what we're looking for A multiplied by U and then A multiplied by V. And you say, okay, well, okay, I got A's multiplied by U's and A's multiplied by V's. That's great, but it seems like really all over the place until you realize that this is the result of the matrix multiplication. All right, so the next line is just basically us undoing the multiplication, which is why I was saying you could work the left side of the original equation or the right side, because sometimes if you work the left side and then a little bit on the right, you can meet in the middle and save yourself some work. It's just I got in a groove with the left side and I was having fun. I like algebra, so sorry. So A1, A2, A3. Multiplied by vector U, which is U1, U2, U3, which ultimately is the same thing as saying AU. And then A1, A2, A3 multiplied by V1, V2, V3, which is ultimately the same thing as A times V. And there's our proof. And again, easier ways, sure. Shortcuts? Yeah, probably. Definitely. Work the right-hand side a little bit, and you could streamline this process, because what'll happen is, if you work the right-hand side, you're going from this to this to this, and then once you get this, you realize it's the same and you're done. All right, so you can kind of get to a point where you're saving yourself a little time, but there's the point behind me showing this stream of consciousness really approach is that there's really no wrong way as long as you're using appropriate algebraic skills, right? And the rules of matrix operations, which you can never lose sight of, because some of them are different enough from ordinary algebra that you'd be like, well, that can't possibly be a thing you could do, and it's totally a thing you could do, all right? So there was a list of properties. I think it was a bunch of pages ago. I can look through and find it at some point, but it said, you know, well, this was one of them, you know, A times U plus A times B equals, you know, and it was a whole list, and it had the identity property and commutative properties and all that. Take a look at those, and anything that looks like it's not common sense, take some time and really think about it and try to think about why that it might be what it is. And also, you know what? Not a bad idea to try to prove it. Because this is the blueprint. You know, you just make up, just be mindful of the space that you're working in. This is 3 space. You could, if you want to dial down the work, dial down the dimensions, all right? Just do the same thing. If you want to do this with a lighter version of this, make it A1, A2, and make it 2 space. The algebra is a little bit easier, and you still get the same, you know, ability to connect the proof to the rule itself, all right? But yeah, these problems are a little bit more algebra intensive. So what I'd like you to do is try this proof for homework, so that again, just like that problem I almost forgot to go over today, you can have an opportunity to experience it first before I spoil it, and then this problem I really like. So let U equal this, V equals that, and W equals that. It could be shown that this relationship is true. I want you to use that fact, but no row operations. And what I mean by that is, if you were to do it by hand, like, I wouldn't want you to put it in reduced row echelon form, which also means don't go putting it into a calculator and putting it in a reduced row echelon form. What you're looking to do is use properties. Maybe one of these 2 properties, to see if you can establish that this is a true relationship based on this information. All right, we'll see if the properties can get us there and save us from having to do row reduction techniques. All right, so that's where we're going to leave it for tonight.